Welcome to the world of geometric complexity. This is an introduction to computational geometry and geometric algorithms. We will explore the fascinating intersection of mathematics and computer science through geometric problem solving. Computational geometry is a branch of computer science that studies algorithms for solving geometric problems efficiently using computational methods. It deals with designing and analyzing algorithms for geometric problems, such as finding the convex hull of a set of points. Some of the key problem areas in computational geometry include proximity problems, which involve tasks like finding the closest pair of points, performing nearest neighbor searches, and constructing Voronoi diagrams. Another area involves geometric structures, such as convex hull construction, triangulation, and line segment intersection. The convex hull problem involves finding the smallest convex polygon that encloses all given points in a plane. Imagine you have a set of nails hammered into a board, and you want to wrap a rubber band around them so that it encloses all the nails. The shape formed by the rubber band is the convex hull. The Graham scan algorithm is a method for finding the convex hull of a finite set of points in a plane. The core steps involve finding the bottommost point, sorting the other points by their polar angle with respect to this starting point, and then building the convex hull using a stack-based approach. The Graham scan algorithm has a time complexity of big O of n log n, reflecting its efficiency in handling large datasets, and a space complexity of big O of n, indicating it scales linearly with the input size. The line segment intersection problem involves finding all pairs of line segments that intersect each other from a given set of n line segments. A naive approach would require big O of n squared comparisons, which is inefficient. Therefore, more efficient solutions are needed to solve this problem effectively. The sweep line algorithm, exemplified by the Bentley-Ottmann algorithm, provides an efficient approach to finding line segment intersections. The algorithm creates an event queue, and then sweeps a line from left to right processing events as it encounters them to find the intersections. This technique is crucial for optimizing the line intersection problem. The code block shows the general structure of such an algorithm. Voronoi diagrams provide a partition of a plane into regions, where each region is closer to one site or point than any other. They have several practical applications, including nearest neighbor queries, spatial analysis, and mesh generation. Essentially, if you pick any location in a region, the nearest site is the one inside that location's region in the Voronoi diagram. In convex hull algorithms, Graham scan and quick hull have a time complexity of big O of n log n, while gift wrapping has a time complexity of big O of nh, where h is the number of vertices on the hull. For line intersection, the naive approach has a complexity of big O of n squared, while the Bentley-Ottmann algorithm improves this to big O of n plus k log n, where k represents the number of intersections, making it optimal for scenarios with fewer intersections. Geometric algorithms have several real-world applications, including computer graphics and gaming, geographic information systems, robotics and motion planning, and computer vision and image processing. Key takeaways include that efficient algorithms reduce complexity, geometric structures enable optimization, the sweep line technique is powerful, and there are trade-offs between time and space. Geometric algorithms bridge mathematics and practical computing solutions. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.